All right, so let me try to get to this concept of cross-validation. So imagine that we've got our data, which is our training set. We can again picture it geometrically in the case of regression, and ultimately what we're trying to do is find a way of predicting values in the testing set. So what we imagine is we do some kind of regression, and we might want to fit this to a line. And the line is good; it kind of captures what's going on. And then if we apply this to the testing set, maybe that it's gonna do a pretty good job. But if we are feeling kind of obsessive compulsive about it, we might say, well, in this particular case, we didn't actually track all the ups and downs of the data. So what could we do in terms of if we fit it with a line and the error is not so great? What else could we switch to, Charles?
We could just use the test set.
No, sorry. What I mean is, if we fit this to a line and we're sort of not happy with the fact that the line isn't fitting all of the points exactly, we might want to use maybe a higher order polynomial
Oh, I'm sorry. I totally
to fit
misunderstood
this
you.
better. So if we can fit this with a higher order polynomial, and then maybe it'll hit all these points much better. So we have this kind of other shape, and now it's doing this. It's making weird predictions in certain places. So really what we'd like to do is, what was your suggestion? If we trained on the test set, we would do much better on the test set.
Yes.
But that's definitely cheating.
Why is it cheating?
Why is it cheating? Well, if we exactly fit the test set, that's not a function at all, is it? We exactly fit the test set, then again, that's not going to generalize to how we use it in the real world. Point that we are assuming that this data is representative of how the system is ultimately going to be used. In fact, there's a abbreviation that statisticians like to use, that we really count on the data being independent and identically distributed, which is to say that all the data that we've collected, it's all really coming from the same source. And so there's no sort of weirdness that the training set looks different from the testing set, looks different from the world, but they're all drawn from the same distribution. Is that we'd like to use a model that's complex enough to actually model the structure that's in the data that we're training on, but not so complex that it's matching that so directly that it doesn't really work well in the test set. But unfortunately, we don't really have the test set to play with, because that, again, is going to too much teaching to the test. We need to actually learn the true structure that is going to need to be generalized. So how do we find out? How can we pick a model that is complex enough to model the data while making sure that it hasn't started to kind of diverge in terms of how it's going to be applied to the test set? If we don't have access to the test set, is there something that we can use in the training set that we could have it kind of act like a test set? Indeed, right? So there's nothing magic about the training set all needing to be used to fit the coefficients. It could be that we hold out some of it as a kind of make-pretend test set, a test set, a trial test set, what we're going to say cross-validation set. And it's going to be a stand-in for the actual test data that we can actually make use of, that doesn't involve actually using the test data directly, which is ultimately going to be cheating. So this cross-validation set is going to be really helpful in figuring out what to do.
And to get into cross-validation, let's first talk about problems with splitting a data set into training and testing data. Suppose this is your data. By doing what Katie told you, you now have to say what fraction of data is testing and what is training. And the dilemma you're running into is you'd like to maximize both of those sets. You want to have as many data points in the training set to get the best learning results. And you want a maximum number of data items in your test set to get the best validation. But obviously there's an inherent trade-off here, which is every data point you take out of the training set into the test set is lost for the training set. So where do you set this trade-off? And this is where cross-validation comes into the picture. The basic idea is that you partition your data set into k bins of equal size. So for example, if you have 200 data points and you have 10 bins, very quickly, what's the number of data points per bin? Quite obviously it's 20. So you would have 20 data points in each of the 10 bins. So here's the picture. Whereas in the work that Katie showed you, you just pick one of those bins as a testing bin and the other 9 as a training bin. In k-fold cross-validation, you run k separate learning experiments. In each of those, you pick one of those k subsets as your testing set. The remaining k-1 bins are put together into the training set. Then you train your machine learning algorithm, and just like before, you test the performance on the testing set. The key thing in cross-validation is you run this multiple times, in this case 10 times, and then you average the 10 different testing set performances for the 10 different holdout sets. So you average the test results from those k experiments. So obviously this takes more compute time because you now have to run k separate learning experiments, but the assessment of your learning algorithm will be more accurate. And in a way, you've kind of used all your data for training and all your data for testing, which is kind of cool. So let me just ask one question. Suppose you have a choice to do the static train test methodology that Kay told you about, or you do, say, 10-fold cross-validation, CV. And you really care about minimizing training time, minimize runtime after training, using your machine learning algorithm to output past the training time, and maximize accuracy. In each of these three situations, you might pick either train test or 10-fold cross-validation. Give me your best guess, which one would you pick? So for each minimum training time, pick one of the two over here on the right side. Obviously, if you want to minimize training time, training once is faster than training 10 times. So it's obviously a train test is probably the better one to choose. If you just want to minimize runtime, well, in each case, you end up picking one machine learning algorithm. I would then say if you just care about minimizing runtime, you might as well get the benefit of 10-fold cross-validation to have better assessment of what's going on. So I would put my cross mark over here, but it's not clear either one could be correct. But if you want to maximize accuracy of your assessment, how good your algorithm is, you definitely go for the penalty of going into 10-fold cross-validation, take the extra time, and you will get a better result.